You have seen in the previous video how we actually utilize least square estimation and how we write least square estimation programming utilizing Matlab software. So now I'm going to show you how to do the same thing using recursive least square. So let's have a look at recursive least square equation. Okay, when you have recursive least square estimation, it is as if having additional data on your least square. So if the previous from the previous example you have yn and also phi n and also beta and also zeta that you have here, okay, when you have recursive least square, it is as if I'm adding another set of data into your system. For example, you already have 4,000 data that you predicted using your least squared. Okay, recursive is just what if I add another additional data to the system. Okay, how does that improve my prediction? Okay, so this is actually more realistic on adaptive control. So you just imagine when you want to actually estimate the model order for your for your system that require adaptive control. It is because the parameter of your model is changing, and it doesn't change maybe it doesn't change dramatically, maybe it change over time, isn't it, bit by bit. Okay, so when it does the changes, when the changes happen, you want your parameter estimation to actually detect these changes and improve your model estimation. Okay, so this can be done if you keep collecting data from the system from time to time. Okay, so for example, as I mentioned earlier, with the example of aircraft is traveling from Malaysia to London, for example. So what happened is that the fuel of the aircraft, okay, is actually reducing from time to time when it's traveled. Okay, so therefore the mass of your aircraft is actually changing. So how do you know the new estimation for your system if it's an aircraft just now? All right, you can only actually know and you can only improve the prediction if you have the new set of data coming in from time to time. Okay, during the traveling, you keep collecting data. What is the input and output of the system? Okay, and from there, your parameter estimation will be improved one after another. Okay, one time at a one estimation at a time, and it will actually improve it from time to time. Okay, so then when we want to write the least square estimation, it is as if you are having only, for example, only one data. So in the beginning, let's say we have 1,000 data for n is equals to 1,000. Okay, so it is just simply is I have, what if I have a data of 1,001 for my input, and I have a data of 1,001 for my output as well. Okay, so how do I put that in my phi and in my y, and how I actually can use that to do another prediction for my system again? So that is actually the basic idea of recursive least square. Okay, but of course, when you want to do recursive least square, you don't have to start with least square. You can start from the very beginning, from your data y equals to 1 until y equals to whatever value that you have from time to time. You can use recursive least square immediately, unlike your generalized least square, isn't it? From the previous example, the previous video, for generalized least square, you need to use least square first, but not for recursive. Okay, so for recursive, you can start immediately using recursive algorithm. Okay, I have the derivation of recursive algorithm here in the slide by explaining that additional data, phi, if I call that phi, okay, so that additional data, I'm going to call that x transpose n plus 1, and the value is just one row of additional data to my system. Okay, so that one row of additional data, okay, when we apply our least square estimation with that one additional row, okay, the new estimation is going to be the previous phi, okay, with additional value of one more row. Okay, the phi this is the phi transpose, sorry. Okay, so x will become just one more data there. Okay, and then phi and another additional data, and that put that in the inverse. So instead of having just phi, so the new value of phi will be phi transpose will be here, and instead of having just phi, the new phi will be phi and also one additional data there, and then you inverse that value. Okay, similarly for your phi transpose here, it will be the previous value with one additional data there. Okay, the phi, because it's transpose, so we put it as the next column. Okay, all right, and then for your y also, okay, you have the previous data of y and then the additional one data afterwards. All right, so from that you're going to do your prediction, then you're going to get the new estimation. So guys, for recursively squared, okay, if you have n data, you're going to have a new estimation every now and then. So it means to say your prediction will be also a lot. Okay, it depends on which data that you use. Okay, so if I have estimate it 100 times, okay, so the parameter beta also I will have 100 beta. Okay, because it changes from time to time. Okay, so this is how you do for recursively squared. Okay, now if I expand the equation, it's going to be very ugly now. Okay, so if I expand the equation, it's going to be this massive mathematical equation that you have here. So I hope you're going to do some revision on this, because it is going to be a bit massive if I have to derive them one by one. Okay, I'm just going to show you that this mathematics is further simplified into this equation here, where I introduce a value of P inverse, okay, P minus 1, and I introduce the value of Kn plus 1, okay, with that value I have in this equation here. Okay, and also my Pn plus 1 is equals to that. When I introduce all these, replacing the value that I have in previously in this slide, replacing all these massive matrix. Okay, so what happened is that when I use this all these three value, replacing the previous matrix, I'm going to actually simplify my beta estimation. Okay, using is going to be this, becoming this new estimation here, where my beta n plus 1 is equals to beta n, which is the old estimation, plus Kn. K is actually some sort of a gain, okay, where the value of K is as I have here in this slide. Okay, that's the value of K. All right, and then that gain is multiplied to my Yn plus 1 minus the predicted output. So the actual output, Yn, minus the predicted output. Therefore, this part here is our prediction error. Okay, so for this system, for the recursive least square. Therefore, it means to say, if I do this estimation and then I do this simplification, I will get the new set of parameter estimation, okay, using recursive least squared, where the new set of parameter estimation is equal to the old set of parameter estimation plus gain, some gain, okay, multiplied by the prediction error. So this is how we improve our parameter estimation. Okay, so that prediction error, let's say there's nothing changes to the system. Okay, when there's nothing changes to the system, the prediction error is 0. 0 multiplied by gain, no matter how big is your gain, if you multiply by 0, it becomes 0. So your new estimation will be the same as your old estimation. Because why? Because the system doesn't have anything changes, isn't it? Okay, but if the system is having some changes, all right, and then your prediction error here will actually find out what is that changes, okay, how much is the changes, and that changes is being multiplied with a certain gain, all right, and then it will be added to the old estimation. Therefore, then you get your new estimation. Okay, it is a bit complicated, but I hope you're going to do a little bit of revision to look at this derivation later on your own, and then try to expand the derivation by yourself. Okay, what I'm going to do is then I'm going to show you how to compute the recursive least squared in Matlab programming. All right, so first and foremost, I'm going to define my P. I have just now P minus 1 and Pn plus 1. So I'm going to mention that the P0 is equals to this matrix here, where I have that value is actually is multiplied with I matrix. You can see I'm going to start with setting the algorithm beta B0 is equivalent to 0, okay, which is not very true, isn't it? Okay, then I'm going to have my p value. P0 is equals to alpha I. Alpha is actually a huge value. Okay, it is showing that a very little confidence that I have for my initial estimation. Of course, the parameter cannot be 0, isn't it? So when I have my alpha is equals to 10 to the power of 6, it is actually showing that I have very, very small confidence on the value, okay, which I know it is not true. Okay, so then what happened is that we're going to use this initial value. All right, so when I have p is equals to alpha I, okay, I is the I matrix, okay, with the only value in the diagonal directions. Okay, so therefore my p0, I will start with 10 to the power of 6 in the diagonal directions. Okay, p0 is alpha multiplied by I. Okay, then for the next cycle, I will compute my Pn plus 1 and Kn plus 1 using the mathematics that I have shown in the previous slide here, isn't it? So, okay, so we're going to then multiply and find out what is Pn plus 1 and what is our Kn plus 1. And using these two values, we're going to estimate our beta n plus 1. Okay, another thing that I want to show you is this lambda here. Okay, lambda is known as forgetting factor. Okay, it is to show that how much data, how much your algorithm, your new parameter is actually forgetting the previous parameter. So how much the lambda is actually the forgetting factor on how much your new estimation forget the previous old estimation. Okay, so if lambda is 0, is actually meaning to say your system is completely forgetting the value. If it's forgetting the value, means it's going to be completely new data on your estimation. If lambda is equals to 1, means to say you really remember the previous value, so there's not much changes on your estimation. Okay, so value of lambda, it is in between. Okay, for lambda, it is actually in between 0 and 1. Okay, so in between 0 to 1. Okay, but it cannot be exactly 0 and it cannot be exactly 1. So really lambda have to start with 0.1, for example, and you have to stop at maybe up to 0.98. Okay, so how do we know which one is the actual value of lambda? You have to trial and error. You do not know what is the actual value of lambda. Okay, when you do your Matlab programming later on, you put the value of lambda there as an estimation. Okay, you're going to then try and error for several estimation using several value of lambda. Okay, right, so using this algorithm, okay, we're going to actually do sample by sample and do our estimation one by one. Okay, and as soon as we get our beta n plus 1, we then add more sample of data into the system. Okay, and estimate that with that new sample of data, what is the new estimation of our system. Okay, so that's what's going to happen. So I'm going to show you now for the Matlab programming, how does it really work. Okay, so this is let's show you what happened is that with this Matlab. Okay, let me just clear the screen by having a function of clear here, and I'm gonna clear the screen by CLC, and I'm gonna close all the figures that I have plotted earlier using close all. Alright, now I'm going to load my recursive least square algorithm. I have written the recursive least square algorithm here. Okay, so I'm going to load that by just doing double click. Okay, so when I double click that M file, so it will appear on my editor file here. Okay, so you can see that my command window have actually moved to the bottom of this screen, right? Okay, again for recursive least square, we're going to do that three thing. We're going to clear, close all, and CLC. We're going to load the data. Okay, so when we want to use algorithm, all right, the data that we want to load have to be in the same folder. Okay, if it's not in the same folder, then you need to define actually where does the folder, where does that data being placed. Okay, then I'm going to use again TikTok, okay, to measure how much time I need to use this to write this program. Then I'm going to write my NP. This is my model number of parameters. So if I use model order is equals to 5, then my number of parameter here have to be 10. Okay, so if I decide that the model estimation is going to be 5, okay, so these have to be 10. All right, so that my MO here is the model order. So it's going to be my number of parameter divided by 2. All right, lambda is, as I mentioned just now, is the forgetting factor. So I'm going to start with lambda equals to 0.1. So it's actually really forget with the previous value. Okay, so is it the correct value? I do not know. I'm just going to use that and then I'm going to change it later on, okay, to another value if it's not giving me a good prediction. All right, I'm going to define the number of iteration as the length of input that output that I have. So y is the output to the system, okay, and x is actually the input to the system. All right, so the beta, I'm going to call it beta n because I'm not going to have only one set of beta like least square. When you do least square estimation, you're only going to have one set of least square, one set of beta, isn't it? But for your recursive least square, beta here, you're going to have a lot because for the new input and output, okay, your beta will be more and more, isn't it? So if you have 1000 data, you can have 1000 set of beta, all right, and because it is actually changing from time k equals to 1 until k equals to 1000 depending on the data that you have. All right, so the size of beta is equals to the number of parameters, of course, multiplied by number of data that you have. Okay, yp is the predicted output. Xn is also again is another matrix that I define here as NP, the model number of parameter, and the size is number of parameter with 1. All right, P here is the one that I mentioned just now is alpha I, where alpha is 10 to the power of 6 multiplied by I matrix. Okay, in Matlab, I matrix is just written as EYE. All right, then I'm going to have this loop. Okay, so P is equals to this value. Then this loop is all the mathematics that I have just now is put in this loop here. You can see I have value of K, value of P, value of Y predicted. Y predicted is just, Xn here is the new value. So as if I have new phi all the time. Okay, so if you look at in the loop, okay, for the for loops, okay, I will start with I equals to MO plus 1, okay, and I'm going to stop until N according to my data. So how many N that I have, okay. Then inside the for loop, I have Xn. Xn is actually a phi, okay, but the value of phi with one row only. So I'm not going to use phi for the lump sum like we have in our least square, but for recursive least square I'm going to use Xn. Xn is actually phi, but only the first row of phi only. So we're going to do phi row by row, not the whole lump sum of phi like we have before. Okay, so we're going to call that Xn. Okay, and this is exactly like what we have in our least square, but you can see that I did not put it in a second row and all. Okay, it's just one row only. Okay, then xx is our estimation. You can see I inverse estimation based on our slide just now. I have that value. I inverse lambda multiplied by p multiplied by xn, and then I have k is equals to this value here, p is equals to this value here. Okay, and then lastly I have yp. Yp is the prediction. The prediction is equals to xn, the new set of new data, multiply the bn plus, you can see that I minus 1 here. Okay, so xn is the new set of data, multiply by bn with the I minus 1. It means to say it is the previous set of data, beta n, the previous estimation. So that will give me my y predicted. Okay, error is equals to the actual y minus the predicted y. It's here. Okay, and then using that error, I will calculate the new parameter bn. I, the new bn, the new parameter bni is equals to bni minus 1, the old estimation, plus gain k, okay, that we have actually defined here just now, multiplied by the prediction error that we have here, error here, okay, the actual prediction error. So that's going to give you the new estimation of your system. Okay, just imagine that this is data is collected from the system from time to time. So the next time when you go for that loop is actually you're going to collect the new set of data, and then you're going to have a new set of data in your xn here. Okay, so the reason why I don't put it, I put it in the loop is because I don't have the actual system running, right? So I collect the data as a bulk data, but in reality, okay, when you want to use your recursive least squared, as if you have your data acquisition and and then you collect the data every now and then, so you don't have to have that loop. You're just going to have data being updated from time to time. Okay, so when I put this in the loop, it is as if I'm collecting data and then I read the data again and again. Right, so then for the next loop, okay, the next iteration, the new xn is actually put into the system as if I have the real system, the data acquisition now collecting the new set of data. Okay, so that xn here is actually defining that new set of data. Okay, so then I will recalculate the parameter using this equation that we have here. Okay, then with that new set of data, we'll get a new prediction error, new prediction, and then new prediction error. And then using that prediction error, we will calculate the new beta estimation. All right. So these will go on and on. The more data that you collect, okay, so this recursive least squared should do your parameter estimation and adjust your parameter every now and then, from time to time. Okay, so then for this, of course, for this example, I already have the set of data. I don't want to attach it to my data acquisition. It's going to be a bit tricky. Okay, so I collect the whole set of data, and I'm just going to put in these algorithms in terms of the loop, okay, as if it is collected by one data at a time. Okay, all right, then I'm going to plot in the figure. Okay, so I have double here. I'm going to delete that. Okay, I'm going to plot in my first figure is the actual and the actual output and input. Second figure is actually my predicted output. Okay, and then the last figure is actually my error, prediction error. Okay, I'm also going to calculate my mean square of error. All right, that's for my recursive least square. So I'm just going to click run here and have a look how does it respond. Okay, so it's responding very fast. Okay, the mean squared error, the time that we have is 1 second to estimate it. Okay, and the mean squared error that we have is 0.0021. Okay, so the mean squared error is actually more than before. Okay, why? Because the estimation doesn't use so much data, isn't it? Even though we use 3000 data, but you can see from when we estimate, we just use one set of the fee is just one row of data, isn't it? Not like a lump sum of data like where we have using our least square. Okay, so let me just show you how does the figure looks like. Okay, so that is the estimation. It's not as good as least square, but it is more reliable because it is more realistic, isn't it? Because for least square, you have to have the whole batch of data, but recursive least squared will enable you to predict with a very minimum data, and the data is coming updated from time to time. So even though the prediction error is more, okay, but it is more realistic on real-time estimation. Okay, so you can see for figure 1 is the actual output and input of the system. Figure 2 here is actually the predicted output and the actual output. Okay, and then figure 3 here is the error prediction, or the prediction error of this estimation. All right, so how does recursive least, can we improve this further? Okay, maybe we can try. Okay, so what you can do is maybe you can try change this value. Okay, So instead of having 3000, let's use 4000, because we use 4000 just now for least square, isn't it? Okay, so let's have a look at what happened with lambda. Let's say I change lambda, not 0.1, maybe I change it to 5. Sorry, 0.5. So lambda value can be from 0.1 until 0.98. It cannot be 0 and it cannot be 1, okay? Because if it's 0, then the data will not remember at all the previous estimation. If it's 1, it means to say it will remember exactly what is the previous estimation. So you're not going to do that, okay, between this value. All right. So I put lambda here. Let's say if I put 0.5, and then let's say the estimation error. You remember just now when we do least square, the estimation is much better when we have a lower order, isn't it? So let's try lower order. Let's use 4. Okay. So maybe let's use 4 with lambda equals to 1 again. Still, okay. Don't choose change both. You change one at a time to check how does it perform. Okay. So let's change the model order to 4, and then let's have a look again with the same lambda. What happened? Okay, so when I run, still the mean squared error is still huge, 0.0019. So it's not improved so much. Okay, with just changing the model order. Let's have a look at what happened when we change the lambda. Maybe I want to use 0.9 instead of 0.5. Okay, so let's run this. Okay, so again it is a mean square error is 0.074. It doesn't improve so much. Okay, so I was expecting a better estimation, but it doesn't improve so much by changing the value of lambda here. Maybe we should change it to 5. Okay, so yeah, lambda is completely unknown, so you can just play around with the estimation and try to get the best estimation, okay, with the lambda and lambda value, and also with your model order. Maybe for this particular system, you know already just now with least square, the estimation with model order of 2 is better. Okay, but for recursive least square, maybe you want to change it a little bit on the value of model order and also the lambda, the forgetting factor. The rest of it, you cannot change so much. Okay, you can change the number of data, but it doesn't affect so much. Why? Because you can see from the loop, the estimation is only using this set of data, isn't it? So in this case, every estimation is just going to use a double of the model order. So for example, if your model order is 4, model order is 2, so the data that you use for estimating is only 4. Okay, then every now and then you're going to update the data, but the data that you use, the number of data you use is always 4 data at a time. Okay, so you're predicting the value using 4 data at a time. Of course, with the loop, you keep predicting it, you keep updating it, but only 4 data at a time. This is not the same as least square, because least square you use all 4000 data in your phi matrix. Okay, so but not the same case with recursive least square. But how come recursive least square is better? Because recursive least square, when you do your prediction, it is mimicking the real system. Okay, when you have a real data acquisition system collecting data from the system. Okay, for adaptive control, of course, you need to collect the data every now and then because your system parameter changes all the time. Okay, so when the parameter of the system changes all the time, the moment you collect the data, that data will actually portray or giving you some trait why the estimation, what happened to the system. So if the characteristic or the parameter of the system have changes, your data will actually have that trait in the data. So when you do your estimation, it should reflect your system, okay, and it should give you a better system prediction, should update the parameter of your system. Okay, so this is how you do it with recursive least square. Let's have a look how does that in your figure just now. Okay, so the figure of your system is like that. Okay, so again, the prediction is not as better as least square, but it is actually mimicking the real system. Okay, so this is why recursive least square is most of the time more desirable compared to least square. Okay, all right, that will be all for